Good morning and welcome to IBM Qiskit seminar series. I'm Alireza Saif, a researcher at IBM Quantum and filling in for Zlatko this week. But don't worry, he will be back soon. And we'll begin soon, but let's give everybody some time to tune in. In the meantime, let us know where you're tuning in from. I can see that people have already started. I'm tuning in from suburbs of Washington, D.C. See that we have people from all around the US. Hi, Kelly. Yeah, and also please use our chat to ask questions live, and I'll bring them up during the talk. All right. So let's give people some time to tune in. Okay. Yeah, so this is our last episode of the year, and I hope that everyone has had a fantastic year so far and have an even better one next year. We will be back starting mid-January, and we have our weekly seminars. These seminars happen every week on Fridays at noon Eastern time. Yeah, and with that, I'm excited to roll out this week's episode of Qiskit Seminar Series, brought to you live by IBM Quantum. I'm your host, Alireza Saif, and it is my pleasure to host Britton Plourde talking about protecting superconducting qubits from environment poisoning. Britton received his PhD in physics from the University of Illinois at Urbana-Champaign in 2000, studying vortex dynamics in superconductors. He then was a postdoctoral scholar at the University of California, Berkeley, where he worked on experiments with superconducting flux qubits. In 2005, he joined the Department of Physics at Syracuse University, where he runs a low-temperature research lab, investigating various aspects of superconducting circuits for quantum information processing. Among his many awards and honors, he has received a Career Award from NSF in 2006, an IBM Faculty Award in 2011, and very recently he has been designated as a fellow of the Institute of Electrical and Electronics Engineers. So how are you doing, Britton?
I'm doing well, thank you. Thanks for the introduction.
Great. And where are you joining us today from?
So I'm in Syracuse, New York, sitting in my office at Syracuse University, so in upstate New York.
Great. So yeah, I guess without further ado, let's start, and the stage is yours.
Super. Well, yes, thanks for the introduction. And it's great to be here today. I'm happy to talk with all of you. And I'll be describing some recent research into environmental poisoning of superconducting qubits. And we'll talk in a little bit about what we mean by environmental poisoning. This is a joint research project between a team of graduate students and postdocs in my lab at Syracuse University, here in Syracuse, New York, and the group of Robert McDermott at the University of Wisconsin in Madison. Okay, so let me start out just with a little bit of an introduction to superconducting qubits. So one of the leading ways to implement qubits for a quantum computer is using superconducting integrated circuits. And these superconducting circuits, people have been working on this for a little over 20 years, and they've enjoyed a really tremendous rise in performance over those past 2 decades. So going back to 1999, when the very first superconducting qubit was implemented at NEC in Japan, a qubit called the Cooper pair box qubit, the performance of the device measured as its coherence time, and so its lifetime, whether you want to call that a T1 or a T2 time, we won't worry about that detail for the moment, but it was very short. So the circuit worked and it was amazing, but it had that it worked at all, that it was this integrated circuit that could behave like a quantum mechanical object, so exist in a superposition of states, but its coherence time was very short at the nanosecond level. But this is a log scale here on the lifetime. So over the ensuing 2 decades, the community has made a variety of improvements and all sorts of work to tackle various problems that limited those coherence times. And now coherence times are 5 or almost 6 orders of magnitude larger. So nowadays, state-of-the-art coherence times for superconducting qubits are in the hundreds of microseconds or even millisecond range. And I should say this graph of this sort of Moore's law of coherence is from a review article from just a few years ago by the MIT group. So these tremendous improvements in coherence over the years have enabled the implementation of relatively large-scale systems of these superconducting qubits, actually building processors. I'm highlighting two here, one from the Google Quantum Information Group of the 53-qubit Sycamore processor that they used just a few years back in their experiments demonstrating quantum supremacy. And then a very recent one from IBM, their new Osprey chip that now I believe has 433 qubits in it. So this is putting us into what people refer to as the era of noisy intermediate scale quantum, the NISQ era. And with these large scale processors, they take advantage of these tremendous improvements in coherence times over the years. And there have been already initial steps towards actually implementing quantum error correction. And you know, there's signs that progress will continue marching forward, and we'll get to ever larger systems. But besides making larger systems, we need to keep extending along this curve here, this trajectory. We need further improvements in the qubit coherence, which can translate into then further improvements in the gate fidelity of the qubits in order to work towards an eventual fully error-corrected fault-tolerant machine. And so one of the topics today is about environmental poisoning of qubits and how that can limit coherence and things we might be able to do to try to mitigate those poisoning sources to make further improvements in coherence. Beyond that, though, we also have to worry about something that hasn't really been a topic, at least in the field of superconducting qubits, until the last just couple years, which is the possibility of correlated errors across an array of qubits. So if multiple qubits or all of the qubits in an array experience some sort of error at the same time, that's a problem that even the best quantum error correction codes that we have available today from a theoretical standpoint can deal with. And so it's fatal to those error correction codes, and the algorithm that's running would have to stop and start over again. So it's very important to understand these correlated errors, what causes them, and figure out things we can do to try to mitigate those correlated errors. Okay, so besides this slide here giving an overview of the field, I want to have just one slide on just the physics of superconducting qubits to make sure all of us here in the call are on the same page. So a superconducting qubit it's an integrated circuit built out of superconducting metals, thin film metals on insulating substrates, typically intrinsic silicon, sometimes sapphire. And so if an electrical engineer were to go and say, try to design a circuit that could make a qubit, that electrical engineer might think of maybe going back to their electrical engineering 101 course and trying to make an LC oscillator, trying to make a very high quality factor LC oscillator. Maybe you would choose to make a superconducting inductor, maybe superconducting plates for your capacitor, choose the lowest possible dielectric you can imagine, and you'd make this great LC oscillator. The problem with doing that is if you then cool that down so that the thermal energy, K Boltzmann times the temperature, is much less than your photon energy, h bar omega, where omega is just, I should have had this written on the slide somewhere, but omega is, of course, 1 over the square root of the product of the inductance and capacitance. You would then resolve the level structure of this circuit, this LC oscillator, but the problem is the potential would be parabolic. This would be a harmonic oscillator, and the level spacing would be equal between 0, 1, 2, 3, all the way up that ladder. And so it would be not addressable as a qubit. You would be able to prepare coherent states, but you wouldn't be able to prepare Fock states and say, put the qubit purely in say, the 1 state or purely in the ground state. And I should say this diagram here comes from an excellent review article from just a few years back from the MIT group. That's a sort of a guide. I believe it's something like a quantum engineer's guide to superconducting qubits. And I would recommend it to people in the audience trying to get some background reading on how superconducting qubits work. So this figure comes from there. So what we need is something to make the circuit nonlinear, to make it an anharmonic oscillator. And with superconducting circuits, there's a very natural way to do this using something called a Josephson tunnel junction. And a Josephson tunnel junction is a circuit composed of 2 superconducting electrodes, so say these 2 blue rectangles here, that are brought up very close together, but with a very thin sort of nanometer scale insulating barrier in between them. So a superconductor, insulator, superconductor junction. And when we do that, if the barrier is thin enough, like a nanometer or so, the wave function for the superconducting Cooper pairs on one side of the electrode can leak through and overlap with the wave function from the other side, and we get a tunnel coupling. And that sort of circuit, it turns out, behaves like an inductor, but it's an inductor whose inductance depends on how much current is going through it. And our circuit element for this type of Josephson junction is simply an X. Okay, and so when we do that, it turns out we get a cosine potential. So it looks like a parabola at the bottom, but of course it deviates away from a parabola as you go away from the bottom. And it turns out that anharmonicity, that nonlinearity, is enough to make the level spacings now unequal. So there's a unique spacing between the ground and first excited state that's different from the spacings for all the other higher levels. And so we can then confine our device to these lowest two levels, say the ground state here and the first excited state. And this ground state will be our qubit 0, and the first excited state will be our qubit 1. And just to put numbers on things, the typical transition frequency is in the ballpark of 5 gigahertz, maybe down to 4, maybe a little above 5, but in that range. The anharmonicity, which is the difference between the 1-2 transition and the 0-1 transition, is typically a few hundred megahertz. And this design of circuit is something called the transmon. This design has been around for about 15 years or so now. It was first developed at Yale. And this is sort of the workhorse qubit that's used by not everyone in the community, but it's probably the majority of superconducting qubit implementations. And just to sort of point at a picture of one, this is one from one of the recent experiments that I'll be talking about in the coming slides. So what we have here is a transmon just like this. So it's what we call a single-ended transmon. And the Josephson junction is too small to see in this image, so it's highlighted with this yellow bar down here. And most of what we see, this sort of plus sign here in lighter gray, that's this shunt capacitor. And it's the capacitance between this electrode and the ground plane out here that gives us this shunting capacitance of the Josephson junction down here. And so this type of picture, that the lighter shade is metal, in this case niobium, and the black region is places where the niobium's been etched away, and we're looking down to the silicon substrate underneath. Okay, so let me move on. That's the basics of superconducting qubits. But now, the main topic of this talk is about environmental poisoning and coherence and changes in coherence in qubits. And so let's just talk just for a minute about decoherence in general in superconducting qubits. And so even more generally, for any qubit, we could represent its state on the block sphere here, where a vector pointing to the north pole would be the qubit 0 state, vector pointing to the south pole would be the qubit 1 state, and any point in between on the surface of that sphere represents some arbitrary superposition of our qubit state. And we can think about decoherence in two different categories. Borrowing from the language of NMR, we can look at T1 type of processes and T2 type of processes. So T1 involves inelastic relaxation, say from the 1 state relaxing back to the 0. And that can be caused by several different things, but probably the two most dominant processes that affect superconducting qubits. One of them is dielectric loss in the materials that make up the qubit, in, say, the substrate, in the metal films, in the interfaces between them. I'm not going to be talking about that today, but that's an extremely important topic that's a very active research by many, many groups. Another piece, though, that can limit relaxation is what are called non-equilibrium quasiparticles, and that is what I'm going to be talking about today. So quasiparticles are dissipative, broken Cooper pairs that can move about in the superconductor and absorb microwave energy and cause this relaxation. The other type of process, dephasing T2 processes, are set by various types of low-frequency fluctuations in the circuit environment, things like magnetic flux noise for flux-tunable qubits, charge noise for charge-sensitive qubits, fluctuations in the number of photons in the readout cavity that's used to measure the qubits. And these, if we translate sort of then into quantum information language, these two T2 processes would essentially be phase flip errors, and these T1 processes would be bit flip errors. Okay, so we're going to focus on non-equilibrium quasiparticles today. And so let's talk just a little bit about what quasiparticles are. So quasiparticles in a superconductor. So a for understanding quasiparticles, we're going to look at density of states diagrams for a generic superconductor. So this is the density of states here running horizontally on this axis, and this is energy relative to the Fermi energy on the vertical axis here. And so, one of the great things about superconductors, the reason they are excellent materials for building qubits, is there's a natural gap in the energy spectrum, a gap to single particle excitations in a superconductor. That gap delta is of the order of about 1/10 to about 1 or a little bit more milli-electron volts, so little m eV. And at zero temperature, all of the charge carriers will be condensed. They'll be paired up into what are called Cooper pairs. And those Cooper pairs will be condensed at zero energy. There'll be this macroscopic ground state that can carry current with no dissipation. But if the system is not at zero temperature, so that there can be thermal excitations, or if there's some absorption of energy, say from photons hitting the superconductor surface or phonons hitting the superconductor surface, if those photons or phonons are greater in energy than 2 times the superconducting gap, so 2 delta, then that quantum of energy being absorbed can break a Cooper pair and generate what are called quasiparticles. One Cooper pair broken will generate 2 quasiparticles that get kicked up here. And how far they get kicked up depends on the energy of the phonon or photon being absorbed. But the key is that absorption of that quantum has to be bigger than 2 delta. And the quasiparticles can rattle around up here. And the problem is the quasiparticles are dissipative. They're single particles. They do carry, and they're single particle excitations above this ground state, and they carry entropy when they move, so they dissipate. And that's the problem. That's why they can impact T1 of the qubit and cause relaxation. Now, when quasiparticles move around, they can scatter and they can lose energy, but they can't get below this gap delta. They can scatter down to what we call the gap edge here, but then they're stuck. They can't be in here because this is a gap to single particle excitations. But what can happen is if there's 2 quasiparticles up here, they can find each other, or if they find each other, they can recombine and reform a Cooper pair. And when they do that, they emit a phonon, and that phonon is going to be at the gap energy, 2 delta. Of course, if they scatter from up here, they can emit phonons of higher energy, but 2 quasiparticles recombining here emit a phonon of 2 delta. Okay. And so in terms of these quasiparticles in a superconductor, we talked about this density of states diagram. One way we can quantify how many quasiparticles are around is to look at what's called the quasiparticle fraction, which is the ratio of the density of quasiparticles by volume to the density of Cooper pairs in the superconductor by volume. Now, as a function of temperature, this is the expression for this equilibrium density of quasiparticles, or fractional density of quasiparticles. And if we put in numbers, so aluminum for the size of its gap, if we work in temperature units, and if we're running on a dilution fridge at, say, the 10, 15, 20 millikelvin kind of range, this number for the quasiparticle fraction is ridiculously small, 10 to the minus 50. So there basically should be absolutely no quasiparticles at these temperatures. But what's observed experimentally is something from, say, about almost the part per billion level, even up to the part per million level of quasiparticles relative to Cooper pairs. And so at this level, there are no quasiparticles essentially. At this level, say the part per million, it starts to matter. And the quasiparticles become a non-negligible contribution to the T1 of the qubit. And if you get even more quasiparticles, say from, and what we'll be talking about, excessive absorption of energy, this number can get higher. And then the quasiparticle loss can actually become the dominant contribution to T1. And so, we mentioned absorption of photons or phonons. And so let's list out some of these here. So phonons can be generated, it turns out, by the impact of various high energy particles, things like gamma rays from background radioactivity in the lab, or the materials that the cryostat or that the sample was made out of, or even from cosmic rays, say from muons. That can be, so this can be a source of phonons, and this is going to be the main thing I'll be talking about for sort of the final third, I don't know what percent, 40% of my talk. But in terms of photons, it's possible, if there are photons around in the qubit environment that are above 2 delta, those can be absorbed directly in the superconducting film and break pairs and make quasiparticles. It turns out there's an even more effective way of photons, though, to break Cooper pairs, and that turns out to be through the resonant absorption of high energy photons by what are called spurious antenna modes of the qubit. And so let's talk about that now. So what are spurious antenna modes of a superconducting qubit? This is a relatively new topic, at least in the community. This was first recognized by my collaborator, Robert McDermott, and his group at the University of Wisconsin, and described in this preprint from earlier last year that these qubits that we make, that we described a few slides back, that we're trying to make these very high Q LC oscillators that have the L of this junction and the C of this shunt capacitor island. And we want it to resonate around 5 gigahertz or so. They work really well, and people can make super LC resonators. But it turns out this type of structure also has some resonances at much higher frequencies that we don't want, nobody ever wanted, and that turned out that are there and have to be dealt with. And so the essential concept is to look at this type of structure here. So we have this metal embedded as a patch of metal embedded in this aperture in the ground plane here. And let's do the spherical cow type of approximation and think of this as a disk of metal. So this dark gray here, and this gray out here is the ground plane. And then the white region is where the metal has been etched away. So this type of structure can also act like an antenna that can resonate, in this case, a patch antenna, where these red lines represent electric fields. So a patch antenna, say, driven by a voltage source down here. It turns out from electrical engineering, antenna engineering, there's something called Babinet's principle that allows us to map this type of aperture patch antenna onto a wire loop antenna as the dual of it. In this case, now we have this gray metal wire loop, and now the red arrows represent current flow around this loop driven by a current source attached down here. And so these type of antenna modes exist, and their wavelength is going to be set, the frequency of them is going to be set by a wavelength being one wavelength around this perimeter here. And so if you take these kind of sizes, sort of for the typical size of a superconducting qubit shunt capacitor and its aperture in the ground plane, that resonance is in the hundreds of gigahertz range, so sort of millimeter wave. So much higher than the actual qubit resonance, the LC resonance that we want for the qubit mode. But it's something that's there. And what was discussed in this preprint is how we can think of the coupling between that antenna resonance, this spurious antenna mode, and the Josephson junction of the qubit. And so that can be modeled this way by writing this circuit as sort of the antenna mode has this radiation impedance here, which in general is something that needs to be calculated numerically. And this is done in the case of this paper, and also in the upcoming work with Robert's group and my group that I'll talk about in a few slides, using a program called CST microwave. But so you can calculate this radiation impedance, and then you can look at its coupling to the Josephson junction described here in terms of its normal state resistance and its junction capacitance. And this gamma reflection coefficient tells us something about the impedance matching between that antenna resonance and the junction. And 1 minus the mod squared of this reflection coefficient gives us the coupling efficiency between the junction and that antenna. And it turns out, sort of by unfortunate luck of how almost every superconducting qubit is made, this coupling efficiency can actually be pretty high. So the qubit can act as a pretty efficient absorber of this millimeter wave radiation that ends up driving large currents through the Josephson junction here, resonant with that hundreds of gigahertz resonance of the antenna mode, and breaking pairs and generating quasiparticles. I should point out that there was some related work a few years earlier from the Yale group in this theory paper that also discussed photon-mediated poisoning of qubits. It just didn't go into this detail of this actual antenna mode being the source of these photon absorption events. So how can we do an experiment to try to study this? So this is part of the joint work between Robert's group and my group. These are some measurements that were performed in Madison, and using, in this case, some qubits that we made here at Syracuse. And the experiment is this: we're going to try to have a qubit, so a qubit, like this, that's going to be represented in blue here, which is going to be the bottom chip in this structure in one of our sort of standard sample holders that we use in our two labs. But then we're going to use a separate chip up here in this upper box, face down towards the qubit, not quite a centimeter away, that's going to be a source of millimeter wave photons that we can control. So we're going to be able to broadcast these high frequency photons from this upper chip and study what happens to this qubit chip that we have down here to study this photon poisoning. And so let's talk about how we can make this source of millimeter wave photons, because we don't have a millimeter wave generator in the lab that we can plumb into our fridge to drive 400 gigahertz photons into our qubit, but we can actually make a local source of those high frequency photons. And the way we do it is simply by using another Josephson junction. And these Josephson junctions actually at the moment are just test junctions, witness junctions that we have on our chip, our qubit chips that we make at the same time as our qubit junctions as a way to characterize the tunnel barrier, so that the junction resistance. But this is the chip that's going to be in this upper part of the sample box up here. We have a wire connected to it so that we can bias the junction. And if we bias the junction up beyond it's to a relatively large voltage, then it'll undergo Josephson oscillations. And Josephson oscillations are described by this simple relation. They'll be oscillating at this frequency, just the ratio of the voltage we bias it to a flux quantum. A flux quantum is Planck's constant divided by 2 electron charges. And so it has this exact number. Okay, I guess I'm rounding, but so not exact, but this number, 484 gigahertz for a millivolt bias. And this ratio, this fact that this is governed by just fundamental constants, is the basis for our Josephson voltage standard. It's what our voltage standard is in the world these days. So what we can do is by biasing this junction up, the junction is going to undergo these Josephson oscillations, and it turns out it's going to act as a source of millimeter wave photons that are going to broadcast from a similar type of antenna mode to what we were describing on the previous slide, the antenna mode of a superconducting qubit. And we'll be able to broadcast narrow band millimeter waves in the hundreds of gigahertz range to our qubit. Okay, and so the experiment we're going to do is broadcast these photons and then look at how the qubit responds. Okay, and the way we're going to measure the response of the qubit is through trying to detect what's called quasiparticle poisoning. So we're going to try to detect the generation of excess quasiparticles in the qubits. And so we talked earlier about what a quasiparticle is and why it's problematic to a qubit, but how do we go about measuring it? I mean, one thing we could look at is just suppression of T1 of the qubit, but it turns out that there's an even more direct and more subtle way to measure changes of small numbers of quasiparticles down to just one quasiparticle in the qubit. And that involves using a technique for mapping the quasiparticle parity onto the one state occupation of the qubit. And what I mean by quasiparticle parity is whether there are an even or odd number of quasiparticles on the qubit island. So on, sorry to flip back slides, but on, say, this island here. And so how we can do that? Well, one issue that I sort of didn't go into detail on my slide about the physics of superconducting qubits, but typically a transmon is built in a regime so that the qubit is completely or almost is exponentially insensitive to charge and to say changes of quasiparticles numbers, so that the qubit energy band that we would be measuring, say the transition between the ground and first excited state, would be independent of this quasiparticle parity. It turns out if you make the qubit in a slightly non-ideal transmon regime, so if we make the ratio of the Josephson energy to the charging energy a little bit lower than normal, then that 0-1 transition of the qubit develops some charge dispersion. In this example here, that charge dispersion is about a megahertz or so. And the mapping technique that I'll describe was first worked out in the Delft group in this paper down here back in 2013. And the idea is the following. We initialize the qubit in the ground state, and then okay, let me describe this slide a little bit better. So this axis here is a gate charge, so an offset charge to the qubit island, which in some cases, if you have a lead that's weakly capacitively coupled to the qubit, you can vary the voltage on it, and then you can tune these energy levels. They'll be 2E periodic, each of them, but they'll be out of phase by 1E. And so say one of these would be the even parity number, so an even number of quasiparticles, the other would be the odd number of quasiparticles. And so when you're at a charge bias, say here, these would have a maximum separation, whereas if you have a charge bias here, they'll be degenerate and you won't be able to tell them apart. But so we're going to do a pulse sequence where we apply broadband, so relatively short pi/2 pulses to our qubit to rotate both parities from that ground state that we initialized in down to the equator of the Bloch sphere. But because of these two slightly different frequencies, one parity will evolve faster around the Bloch sphere and go this way. The other will evolve more slowly and go this way around the Bloch sphere. And if we wait for exactly a quarter of a period, so when this point's gotten to here, this parity's gotten to here, and then we apply another 90-degree pulse, but now about the orthogonal axis. So if we initially rotated about the x-axis, now we rotate about the y-axis, we'll map the blue parity down to the 1 state and the red parity up to the 0 state. And then we just do a qubit measurement and we'll get a 0 or a 1. And so if we just repeat this process a bunch of times, say 10,000 times, 20,000 times, whatever you want, each time we're going to get a 0 or a 1. And so we'll just get a string of 0s and 1s at some rate given by our sampling rate, which could be as fast as, say, tens of microseconds, or it could be tens of milliseconds. It depends what we're looking at and how fast the quasiparticle is switching. And so we'll essentially get a telegraph-like signal up and down between 0 and 1. We can compute the power spectrum of that. And in general, it's going to be a Lorentzian type of shape that can be fit by this simple equation. It's going to have some white noise floor out here that characterizes the fidelity of how well we're able to map parity onto the 0-1 state of the qubit. And then it's going to have this knee, characteristic knee at low frequencies that's going to sort of characterize the rate at which the quasiparticles are switching. So in this example here, it's relatively high. It's a little over 100 hertz or so. But that's sort of our characteristic then of how fast quasiparticles, the parity of quasiparticles are switching. So how fast they're moving on and off at that island. Okay, and so here's this experiment for detecting this photon-mediated poisoning. So remember the setup, we've got these two chips, these injector junctions that are in this top chip facing downwards in our sample box, and then the qubit chip in the bottom holder facing upwards. So they're looking at each other about 1 centimeter apart. And if we bias up this injector junction up here, it's going to broadcast photons at a frequency proportional to the voltage that we're biasing it at. And then we're going to measure the quasiparticle parity rate. So this gamma p is the knee frequency that we would measure from this quasiparticle parity mapping sequence. And so along here, we're looking at the frequency in gigahertz that we're broadcasting based on our voltage. And the curves plotted up here are theoretical curves calculated from numerical modeling of the antenna mode structure of the transmitter junction. So that's in red. So it has its own sort of resonance and some structure in it. And then the receiver antenna. So this calculation of this qubit antenna mode, which has its fundamental resonance given by one round trip around this aperture that's right here around 270 gigahertz. It's got a broader feature out here, and it's got some wiggles on it that you could say, is that noise or interference? It turns out that's actually real structure that comes from coupling to a slot line mode caused by the readout resonator, which is what's going off here on the top of this picture. And that actually is captured pretty well by this modeling. And now the purple curve is then the product of these. So the red curve is how efficiently we can broadcast these millimeter waves, and the blue curve is how efficiently we can absorb them. And to compare with the measurement, we want to multiply the two together. And then down here, if we jump to this lower plot, the black dots are the results of measuring this quasiparticle parity switching rate as a function of the frequency that we're broadcasting. And you can see, okay, it can be low over here, but then we get a peak, and then we get a really big peak right here, right around 270 gigahertz, comes back down, and then it trends upwards at the end. And now with this purple curve up here, we can then calculate theoretically what that parity switching rate should be. The one scale factor that needs to be included is just a photon loss factor for photons to not make it from this chip up at the top to the qubit chip down here. So say get absorbed at the walls or by connectors or whatever. And then you can get an actually pretty nice fit to the data, even capturing almost quantitatively some of this fine structure that's in the data. Okay, so this is a way to see directly how these high frequency millimeter wave photons are breaking pairs and making excess quasiparticles in the qubits. And so a further step in the same paper, and I should highlight this is all described in this recent preprint from our two groups. This next part involves also measurements in Madison, but now using some chips that were also made in Madison. So instead of the plus style qubit island, these now have disk style qubits of different sizes and different sizes for the aperture. So there's one with a really big disk and aperture, medium size, and a really small one here. And then a slightly different configuration for the photon source, the broadcasting antenna up here. And these are, again, theory calculations of modeling those antenna modes. And as you might expect, the biggest qubit, physically biggest qubit, has the lowest frequency resonance, close down towards 100 gigahertz. The smallest qubit here in blue has the highest frequency resonance. And the experiment then is, again, measuring this quasi-particle poisoning rate as a function of the broadcasting frequency from the poisoning junction up here. And okay, there's not a perfect quantitative match, but qualitatively it looks pretty good that the really big qubit indeed has this peak down here near 100 gigahertz. The medium qubit has a peak sort of in the middle around 200 gigahertz. And the smallest qubit, the peak is up here well beyond 300 gigahertz. So if you want to push your antenna resonance up as high as possible, you would make the qubit sort of as small as possible. And we can notice one other thing that happens. We can look at sort of the baseline rate when we're broadcasting at frequencies below 100 gigahertz, which is about the aluminum gap, so where we're not breaking any pairs. And so here we're just looking at sort of the background. So quasi-particle poisoning that's not caused by our injection of photons. And we can see the biggest qubit has the highest background rate, up close to 1 kilohertz, whereas the smallest qubit is almost 2 orders of magnitude lower, down near 10 hertz. So that also suggests if we want to make qubits that are more and more insensitive to quasi-particle poisoning, we want to make the qubits as small as possible. Now, those of you that are in the superconducting qubit field recognize that that's also kind of a bad idea. So a lot of the learning over the years that led us to making these significant improvements in qubit coherence within the quantum information community involved making the qubits physically bigger and spreading out the electric fields. That's to make the qubits less susceptible to dielectric loss. And so there is sort of an inherent tension in here that needs to be worked out between this drive to making the qubits smaller to push these spurious antenna modes as high in frequency as possible versus making the qubits as big as possible to spread out the electric fields to minimize dielectric loss. And that's something that needs to be worked out in the coming weeks, months, and years. So this is, I think, a natural break point, because I'm going to move on to now the topic of phonon-mediated quasi-particle poisoning and correlated errors. So if there are any questions that can't wait till the end, I'm happy to take a few questions now.
Okay, yeah. Folks, please type in your questions in the chat. In the meantime, I can ask some questions. First one is, like, you get these rates for your quasi-particle poisoning. Can you also translate these to the expected T1 or T2 that you expect to be affected by these quasi-particles?
That's a good question. In principle, we can, but it's a non-trivial mapping. So the fact that we measure, say, an elevated quasi-particle poisoning rate here means that there have to be some excess of quasi-particles. They're going on and off the island faster. But how exactly that translates into the change in T1 requires mapping this onto an actual density of quasi-particles in the junction electrode of the qubit. And that depends on a detailed model for the actual quasi-particle dynamics, how quickly the quasi-particles scatter down to lower energies where they could get potentially trapped in defects, how they recombine with other quasi-particles and emit phonons. And that's a non-trivial thing. It's not impossible, but it's also going to depend on it's not going to be a generic thing. It's going to depend on the details of the particular superconducting electrode for the junction and what the environment looks like nearby.
I see. And I also noticed that you had listed quasi-particle poisoning as a source of both T1 and T2? Are there two separate mechanisms that from these sources that change affect
Yeah,
them?
so I did put it in the T2 column, and so it does matter. So if you have fluctuations in the quasi-particle number, that can cause fluctuations in the qubit frequency, which will cause T2 errors. But I would say, and the reason I put the circle around the quasi-particles in the left column is the much more significant impact, the more immediate impact right now is on T1.
I see. All right. Thank you. I don't see any more questions in the chat. I guess I can proceed with the second part.
Okay, sounds good. So let me now move on to another topic of environmental poisoning of superconducting qubits. And this is something that's just been recognized in the community just in the last couple of years, that superconducting qubits can exhibit correlated errors where multiple qubits on the chip have an error at the same time. And I'm highlighting here two papers from early 2021, one from the Google group here on the left, and one from the McDermott group at Wisconsin on the right, looking into this. And it turns out the source of these correlated errors in this case is from impacts of high energy particles. So things like gamma rays coming from background radioactivity, and also coming from cosmic ray muons hitting the chip. And in the case of this Google experiment, what they measured was a large array, I believe one of their 53 qubit arrays, and they were doing repeated T1 measurements across some significant fraction of that array. And what they saw were occasional events where many or even all of the qubits that they were measuring would have a sudden suppression of T1, well below the baseline level of T1 in the qubit, that would essentially cause very enhanced bit flips of the qubits. And then the system would recover back to that baseline level, in their case on the time scale of tens of milliseconds. But these events on the scale of tens of milliseconds are actually relatively rare. They happen for the chip in the Google setup roughly once every 10 seconds or so. And in this experiment in Madison, they looked at correlations of errors initially correlations of charge jumps sensed by these charge-sensitive transmons that are again made in this regime where they have some small charge sensitivity to their energy bands. And they could see that qubits that were relatively close together exhibited jumps that were correlated, and qubits that were further apart didn't have very many jumps that were correlated. But as we'll see in the next slide or two, they also were able to look at T1 and see impacts on T1 that could be correlated across the array. And so I'm going to talk a little bit about this experiment from the Madison group before I move on to the new work of how we can actually think about mitigating this type of poisoning. Okay, and so again, this is from this paper from Robert McDermott's group from last year, looking at these correlated charge jumps. And so it turns out with these charge-sensitive qubits, besides measuring the quasi-particle parity as a function of time, it's also possible to measure the offset charge sensed by a given qubit as a function of time. And this, using a very similar but slightly different modified Ramsey type of interference experiment. And so this is a plot of the measured offset charge as a function of time over 10 hours, sensed by 4 different qubits in this array, where the furthest qubit, I believe this diagonal pair here, the blue and the magenta, are about a little over 3 millimeters apart. And the closest pair here, the red and magenta one, are about 300 microns apart. And so each qubit exhibits these sort of stepwise jumps in the offset charge that it senses. And I should say these types of jumps have been seen in other works, including these ones up here. Okay, and the interesting thing is that for qubits that are close together, like say this pair down here, or this pair, the pair up here, so about 300 microns apart, about 600 microns apart, these jumps are pretty correlated. Like a lot of times one qubit has a jump, its partner nearby has another jump. Okay, so there's some interesting correlations, but they're not perfectly correlated. Like here, this one jumped, but this one didn't. But if they look at the qubits that are opposite, that are far apart, they don't see so many correlations in the jumps. So that's interesting. But then what they're able to also do is use these charge jumps on one qubit, in this case, let's say the blue qubit here, as a charge trigger. And they could then trigger on that charge jump and look at T1 on 2 of the other qubits. So in this case, Q2, the sort of teal one up here, and the magenta one down here. And so this curve up here shows the charge trigger. So when a charge jump happens on Q1, they see a simultaneous suppression of of the T1 of the relaxation time on these other 2 qubits, including one of the qubits that's 3 millimeters away from the one that had the charge jump. So this T1 suppression seems to be tied to this charge jump, and it seems to be sort of a global phenomenon across the chip over distances of greater than 3 millimeters. Okay, and so what is the picture here? Well, so the picture is that one of these high energy impact events deposits a lot of energy into the chip, somewhere in the order of 100 kilo electron volts, even to a mega electron volt, capital M. And these events, for a typical chip size here, chips that are maybe 8 millimeters, 10 millimeters across, these events are of the order once every 10 seconds or so. So relatively rare, but they do happen. And when this impact happens, it generates this very high energy burst inside that initially makes electron hole pairs in, say, the silicon substrate, and those electrons and holes can diffuse depending on the band structure of that substrate. And if they happen to diffuse near a qubit, the qubit, if it's charge sensitive, can sense that charge motion, and that's what causes the charge step, because the charges are going to diffuse, but they're eventually going to trap in random defects in the substrate. And where they trap, the qubit senses that, and that gives the step. But those electrons and holes, some of them recombine, and also as they're moving, that recombination and that motion can radiate phonons, so quanta of sound that are radiating, and those phonons can be very high energy, well above the superconducting gap, and they bounce around throughout the substrate. They bounce off the bottom, they can hit the top, and when they hit the top, this is where the device layer is, where all the superconducting thin films are. Because they're well above 2 delta, they break Cooper pairs and generate quasiparticles. And so, as I mentioned, this has got a lot of interest in recent years by various experiments, including many looking at qubits, but also some looking at resonators. So you can also see this effect if you repeatedly measure resonance frequencies and Qs of resonators. And so the question is, how can we deal with this? Because if these phonons are growing everywhere, they can in principle break pairs in most or all of the qubits and cause this temporary suppression of T1. And so, one way you can imagine is trying to get rid of the offending particles, these high energy particles. If you're worried about muons, you can imagine going deep underground, a mile or 2 beneath the Earth, to have the Earth block the muons for you. It's not super practical to put your dilution refrigerators and your quantum computers miles underground, but that's one option. But the problem is muons aren't the only issue. Gamma rays turn out to be an even bigger issue than muons. And the gamma rays can be coming from all sorts of just background radioactive contamination, say in the concrete that makes up the lab, or the materials that make up the cryostat or the chip holder or whatever. And that's even a lot harder to get rid of. So unless you take extreme pains, these poisoning high energy particles are going to be there. You can imagine micromachining the silicon or whatever the substrate is to try to block the phonon motion. That's something our team, my group and Robert McDermott's group are working on currently. Or you can try to channel the energy away from of these high energy phonons away from the qubit and down convert the phonons to lower energies. And that's what we're going to focus on for the remainder of this talk. And the idea to do this was proposed in this paper last year by John Martinez. We're going to take the approach of trying to put large reservoirs of normal metal on the backside of the chip. So these are, should have said, these are sort of side view, cross-sectional views of the chip. So the superconducting films are up on the top surface, say the qubit junction is here. So a gamma ray that comes in makes this burst of phonons that bounce all over. When they hit the qubit, they make quasiparticles. But if you have, say, some normal metal down here, when phonons bounce and go into that normal metal, if the normal metal volume is large enough, those phonons can scatter inelastically off electrons, conduction electrons in the metal, and come back at lower energies. And if they scatter far enough down to energies below the superconducting gap, then when they come back in, they're innocuous. They aren't able to break pairs in the qubit up here. Now, the challenge is at millikelvin temperatures, the electron-phonon interaction rate is pretty weak. So to enhance the probability of this scattering process that we want, we need relatively large volumes. So sort of a rough order of magnitude estimate says that you need roughly 10 microns of thick copper on the backside to do this. Now, I'll mention an alternative. Besides using copper, a normal metal, you could also use a superconductor that's just a lower gap in the junctions. And that will, in principle, do something similar. And this has actually been studied, not with qubits, but with resonators, that you can also use lower gap superconductors to downconvert phonons that poison resonators. But we're going to focus for now on this normal metal approach. And so, here's what we have to do. So our experiment is we're going to try to make a chip that's our control chip that doesn't have any type of structure for downconverting phonons. And it's going to have qubits up here and ground plane. But besides waiting for gamma rays to hit the chip, which we don't have any control over where they happen, when they happen, or their energy, we're going to also have a way to controllably inject phonons. So just like in the earlier experiment, we could controllably inject photons to poison through this spurious antenna mode. Here we're going to use tunnel junctions that are actually on the same chip as the qubit as a source of phonons. We're going to do it by pulsing the bias of this injector junction up above the superconducting gap, which breaks pairs in the junction. But these pairs rapidly recombine. And when they recombine, they emit phonons that couple into the substrate, and they bounce around, and they can bounce over to our qubit and then poison the qubit. And so we're going to have a chip with an array of qubits on it that we can do all of this. But then we're also going to have a chip that looks essentially the same, but then also has this copper on the backside for doing the phonon down conversion. And to make this 10 micron thick copper, we use an electroplating technique to deposit these very thick layers of copper that are thicker than you'd ever want to deposit, say, by evaporating or sputtering. And I should mention this work was very recently published just last month in this paper up here. Okay, and so what does the top side of the chip look like? So I showed you the picture of the back side with the copper metallization. On the top side, we have an array of qubits. So we're going to focus on these three here that are labeled QA, QB, QC. Each one has its own readout resonator that we can multiplex and do readout through a common feed line. And then we have injector junctions, these sources of high energy pair breaking phonons that I mentioned. In the case of the chip that doesn't have the copper, the control chip, we're going to use this injector junction up here to broadcast phonons through the chip. In the case of the chip that does have the copper down converting structures, we're going to use this red injector junction to broadcast phonons from this point. And we'll be measuring the impact on these three qubits. Let's see, I should mention the color scheme. Throughout the remaining slides, I'll be using red to highlight the chip that does not have the copper on it. I think I just said things backwards before, so excuse me. Red is the chip that does not have the copper. Blue is the chip that does have the copper on it. And the qubits, here are just some vital statistics of them. They're in sort of the ballpark of 5 gigahertz. T1s of the qubits are pretty good, but not state-of-the-art. They're 20 microseconds or so. The ground plane on the chip is niobium, but the Josephson junctions are conventional. And the injector junctions are also conventional aluminum junctions with niobium pads. Okay, so the first experiment we do, before we look at quasi-particle parity, we're just going to try to measure T1 directly, and we're going to look at changes in T1 when we inject phonons into the chip from this tunnel junction around the side. And what we're going to be looking at is changes in the T1 rate. So we're going to measure T1 with no injection to get a baseline number, and so take 1 over that to get its rate. And then we're going to measure the change in T1. So the T1 that we get now when we inject at a particular energy, and look at the difference between those. So the change in the relaxation rate. So if this number is big, that's bad. That means T1 got worse. We made the qubit a worse qubit. And so the first measurement we're going to look at over here on the left is we're going to inject, in this case, at a millivolt, so well beyond the aluminum gap of our injector junction. So we're going to inject a lot of phonons, and the duration is going to be 10 microseconds. So we're going to inject a burst of phonons, and the number of phonons is going to be proportional to that width of that burst. But then we're going to vary a delay time to where we do a simple T1 measurement. And then we're going to plot this. And so for the red chip, which is the non-copper one, the one that doesn't have these phonon absorbing structures, we can see that the delta gamma increases. So T1 is getting worse for the first 30 or so microseconds. And it reaches a maximum badness up here, corresponding to T1 dropping down to just a couple microseconds about 30 microseconds after the end of this injection pulse. And then after that, it gets better. It recovers, and it recovers back to the baseline level with an exponential decay where the characteristic time constant is just about 60 microseconds. So that's the time for these injected phonons to dissipate and get out of the chip somehow, say through the point where the chip is anchored to the sample holder, through wire bonds, through other loss mechanisms. If we look at the same measurement for the chip with a copper on it, so the down converting structure, so in blue down here, we can see almost no change. So we inject the same way, but nothing happens. T1 doesn't really change. So it looks already like putting this metal on the backside is doing something significant. We can now also look at, and I should say here, this peak here, we can understand this peak of 30 microseconds after where the poisoning is the worst is about the time that you would estimate for phonons to diffuse from that injector junction over to the qubit junction, undergoing boundary limited diffusion based on the speed of sound in the silicon and the distance between the injector junction and the qubit. But now if we sort of fix our time, our delay time at this 30 microseconds here, and now we vary the amplitude of our pulse that we're injecting at. So here we're fixed at a millivolt, always injecting, but here we're going to scan from 0, no injection at all the way up to 2 millivolts. We can see, and now we're going to look at the same quantity, this poisoning, this impact on T1 on a log scale as a function of that injection voltage. If we're injecting below 2 delta of the superconductor, so about 400 microvolts, we don't see really any poisoning. We're down in the noise, basically. But for the chip without copper, when we get above 2 delta of that injector junction, above 400 microvolts, we see delta gamma rises very quickly, or T1 drops very quickly. And then it just keeps getting worse as we go gradually up. We're injecting phonons at a higher energy and more of them because we're going further out on the IV curve of the injector junction. Now, if we compare that with the chip with copper, over here, we were looking at a 1 millivolt injection. So right here, where there is this really significant difference, not quite 2 orders of magnitude difference in the poisoning level. But we see something interesting if we look at lower voltages. There is poisoning, but it has this very different behavior. Instead of this sharp rise at 2 delta, we see sort of a little bit more gradual but peaked rise right around just under 600 microvolts. And then it improves again as we go past that. It turns out this is actually the first topic that I talked about of this photon-mediated poisoning. And it's the fact that we're using a Josephson junction to do our injection, and we're not only injecting phonons into the substrate, but we're also broadcasting the same sorts of narrowband Josephson radiation photons that I described earlier, and those can couple over to the qubit. And this peak is when we're broadcasting at 270 gigahertz of Josephson radiation, which happens to be the resonance frequency, the spurious antenna resonance frequency of the qubit that we're looking at. So we're measuring essentially the same physics here with this peak in the blue data that we saw earlier in our other paper, which I remind you of the citation here, by photon absorption. So this is not a phonon-mediated process. And once we get past that, then the loss, again, is relatively low, and we don't get see much of an effect of the phonons. So now, besides looking at impacts on T1, we can also look at this quasi-particle parity switching that we discussed earlier for the photon-mediated experiment. But now we can do this here with this in this chip where we can do injection of phonons. But let's first look at no injection at all. Let's just look at baseline levels. And so we're going to do this same parity mapping sequence to map quasi-particle parity onto the 0 and 1 state of the qubit, and then do that repeatedly, compute a power spectrum. And we're going to look at the power spectrum for one of the qubits on our chip that doesn't have the copper, the control chip, and then an example of the power spectrum on a chip that does have the copper structures. And so for both of them, we can see this characteristic Lorentzian. You see slightly different white noise floors here, the two. That's just because the readout fidelity on the chip without the copper is a little bit better, just because of where the parameters are, how we had it tuned up, compared to the chip with the copper. But that's the only source of this difference. The key takeaway difference is the difference in the noise in the knee frequencies. And we can see for the chip without copper, we get a knee frequency a little bit about a third of an inverse second. And I'll say this is already about state of the art. And I refer you to two papers from just this year, one from IBM and one from this paper down here that just came out in the last few weeks that measured times also of about 1 inverse second. And so this is about state of the art for these switching rates. So this means the qubit environment is very quiet, at least up in this hundreds of gigahertz range. And it also helps that these are relatively small qubits with this high antenna spurious rate, spurious antenna frequency mode. But now we can look at the chip that does have the copper, and we can see that this characteristic quasi-particle switching rate is even lower, more than an order of magnitude lower. So an order of magnitude better than the state of the art. So that putting this copper on is already doing something significant to the baseline quasi-particle switching rate. But now with these really low switching rates, it allows us to actually just look at switching directly in the time domain. Okay, so we can look at traces like this as a function of time over just a few seconds here, and we can see switching of the parity, say from even to odd and vice versa, and back and forth. And the experiment we're going to do here is go back to injecting phonons. And so we're going to inject in a pulsed way at a fixed rate. We're going to inject at 20 hertz, but we're going to, and a fixed amplitude, so at a millivolt, where we know we're injecting phonons. We're well above the aluminum gap. And we're going to vary the duration of this injection pulse. And the duration is going to be proportional to the number of phonons that we're injecting. And then in between these injection pulses that, again, are happening at a rate of 20 hertz, we're going to measure the parity at a period of every 100 microseconds. And so if we inject enough phonons, so a wide enough duration pulse, no matter what we're doing for down converting the phonons, there's going to be phonons that'll make it from the injector junction to the qubits and cause poisoning. And what we're going to look at is as we go to wider and wider injection pulses for both qubits, the red being the non-copper, the copper blue being the copper qubit, we can see that at very narrow pulses, the switching isn't that frequent, although it's more frequent in the chip without copper, because what we just saw on the last slide, there seems to be faster quasi-particle poisoning without the copper. We go to really wide pulses, we see lots of switching on both of them. And then in between, we see something in between. But what we can do is quantify that and calculate the switching probability for the parity to switch as a function of per injection pulse, as a function of the width of that injection pulse. So how many phonons we're injecting. And we can see they both saturate up about 1/2, about 50%, which is what we expect, because for some quasi-particle poisoning event where we've got a burst of phonons hitting the qubit, we would expect the parity to get scrambled, not just for one switch, but very fast, probably to switch back and forth, even odd, at a much faster rate than we can measure. Again, we're sampling at 100 microseconds here. But so we're only going to see the events where there was an even number of parity switches, or sorry, an odd number of parity switches. So it came back in a different parity from what it started in. We'll be blind to the events where there's an even number of parity switches. So we expect this saturation at 50%, which is more or less what we see. But we can see that also that to go from the baseline levels up to this 50% level, we have to inject about 20 times more phonons for the chip that has copper compared to the one without. So we can use that as a rough way to quantify and say that, okay, our copper is about 95% efficient at down converting the injected phonons. Okay, and just in the last, I think 2 or 3 slides here, just the last measurement I'll talk about is now looking at this quasi-particle parity, but now again turning off the injector junction. So we're not injecting phonons, we're just looking at background events. And now we're going to do multiplex readout of the 3 qubits simultaneously on the chip, and we can get simultaneous multiplex readout of the parity on these 3 qubits. In this case, we're looking at an example of just a little under a minute trace from the 3 qubits on the non-copper chip. So we can see they all undergo this parity switching, but then we can go through the data, and much longer data than this, hours or even days worth of data, and look at events where there's just a single qubit switching, or look at events where there's, say, 2 qubits switching, but not the third, or a 3-fold correlated events where all 3 qubits switch the parity at the same time. And we can go through and pull out the rates of those 3 type of events and compare between the non-copper chip, again in red, with the copper chip in blue. And so the 3 panels here for these different bar charts, the left panel is looking at the single qubit parity switching events. So we're just one qubit is switching, and we can see what we already saw earlier, just presented differently, that we get a little bit more than an order of magnitude reduction in the parity switching rates for the chip that has copper compared to the one that doesn't. But then in the middle panel, we're looking at twofold correlated parity switching events. So where a pair of qubits had the parity switching at the same time, and we can see that that rate on the copper chip is about 2 orders of magnitude lower than it is on the non-copper chip. And then we can also look at threefold correlated events where all 3 qubits switch their parity at the same time. And we can see that's also about 2 orders of magnitude lower than on the chip without the copper. And so this is good. We're happy. That seems like the copper is really doing something significant, down converting the phonons and reducing these correlated errors, this is correlated parity switching by 2 orders of magnitude. And that's a particularly significant amount from the standpoint of thinking ahead to future devices for implementing error correction. And the simple argument is the following. If we think of, for say, building a processor for future implementation of error correction, let's say we want our single qubit errors to be better than 10 to the minus 4. Well, then for our error corrections to still work, we're going to need to have correlated errors between 2 qubits. So not errors in a 2-qubit gate, but say errors between 2 single qubits, but that happen at the same time in a correlated way, to be less than 10 to the minus 8, because there's going to be random errors between 2 qubits that are going to be at the 10 to the minus 4 squared or 10 to the minus 8 level. And that's actually, I should say, what these black bars correspond to. So these would be the random seeming correlations, the random double parity switching in this case, or triple parity switching in this case, that you'd expect just based on these single switching rates. And you can see our bars are above that we do see excess correlations. So we're going to need the correlated rates to be better than 10 to the minus 8. And if we map that onto, say, a surface code running with a 1 megahertz duty cycle, that would put us, we need to be better than this level here. So without the down conversion, we're worse than that by about an order of magnitude. But with the down conversion, we're better than that by an order of magnitude. So we've reduced the correlated errors to the level where, at least from that standpoint, you could think about moving ahead with implementing a surface code. And so let me just put up my conclusions, and then I'll conclude. So I've told you about environmental poisoning of superconducting qubits, and I've shown you an experiment where we can inject photons at very high frequencies up in the millimeter wave regime and study the quasi-particle poisoning through this spurious antenna mode absorption of high frequency photons. And that's described here in this paper. And I've told you about our experiments studying this phonon-mediated poisoning and ways to mitigate phonon-mediated poisoning to down convert phonons and reduce correlated errors from this absorption of high energy particles by the chip. And that's described by this recent paper. And I will stop there and take questions. So thank you.
Thank you for the great talk. Yeah, there are many questions in the chat. I'll read them to you. Some of them are already answered by the community, but I'll ask them anyway to get your input on.
Okay.
So I guess the first question is regarding the first part of the talk. Okay. The question is, does the arrangement, the physical spacing between qubits on a quantum chip change, decrease, or increase poisoning on a qubit?
So this is in terms of this photon-mediated poisoning.
Yeah, and I guess they're asking about situations where you have more than one qubit. I believe you only considered one qubit that you're looking at, but if you have more than one, then I guess the question is, does the arrangement or distance between them affect this type of poisoning?
Right. So in this case, the experiment, the chip was basically the same layout as the chip I showed later in the phonon-mediated poisoning part of the talk. But the measurements here, say like this measurement, was just measuring 1 qubit at a time. And this particular experiment was done in the McDermott lab in Madison. But they weren't measuring simultaneous poisoning of qubits. But the idea is that they should be poisoned simultaneously here. The photons are getting broadcast from this upper chip, and they're essentially filling up this entire cavity in here with photons, and the polarization is essentially randomized. So we would expect that the position of the qubits down here won't matter. They'll all be getting poisoned.
I see. Thank you. And the same commenter is asking, how could one reach out to you? That, for example, email that you would feel comfortable sharing. So if that's something you're comfortable with, you can.
Sure. So my email address at the university, which, I mean, we could put it in the chat. I actually don't, because of the way I'm sharing right now, I don't have access to the chat, but it's available, on the university website. So
I'll do that. Thank you.
Sure.
So, okay, going to the next question. So they're asking, maybe I missed it, but I'm wondering, for the first half of the talk, did they look at floating designs as well? I recall that IBM has seen very slow quasi-particle tunneling rates.
Yes. So, I mean, in this case, this was a single-ended design. But I will say, in our case, in this later, okay, I don't want to jump around too much, but let me first say, I refer people to this paper here, this preprint from Robert McDermott's group from earlier last year, where this was sort of a theory paper kind of describing this mechanism for these spurious antenna modes. And there they actually modeled a range of qubit geometries. They thought about this patch antenna sort of design, the XMON type design like this, both single-ended. They also looked at like a differential floating transmon design, like a more typical in the IBM style of qubits, and even a 3D qubit, which is also, differential floating design. So those are all described here. But from the other part of the question about sort of the poisoning rates, so I'll jump here for a second. So these were the measurements done in my lab in this experiment on the phonon-mediated poisoning, but this is, again, with no injection. This is still the same single-ended XMON style design, where we're getting these, sub 1 inverse second rates, which are on par with these sort of best that I'm aware of. So including one from the IBM group here, this reference. So it's not clear that mechanism, I mean, it's true, there could be some subtleties to differences in these spurious antenna modes, whether you have a single-ended XMON style qubit versus a floating differential qubit. But both are susceptible to this antenna absorption. The physics is a little bit different, but it's not clear yet if one is better than the other.
Okay. And the other question is there data on how much quasi-particle poisoning is happening on current transmon types that are in production? I guess,
that's a good question. I guess a question for somebody that's in qubit production. So in my lab here at Syracuse, we're not trying to build an entire quantum computer. We're studying physics of relevant to superconducting qubits and like this. So we're not making tens or hundreds or thousands of qubits at a time. I mean, there are measurements. I don't remember offhand in this IBM paper how many qubits were being looked at on a chip. There is this very recent paper from the IBM group I'll point to here, from I think just a few weeks ago, where they looked at this poisoning effect of particle impacts, and that one I don't think they were measuring quasi-particle parity rate. They were looking mostly at, and this is something I didn't go into, but I'll mention it now. They were looking at interesting correlations between the offset charge jumps that are seen, these sorts of charge jumps that have been seen by several different groups, including us. I didn't talk about that, but in our phonon-mediated experiment, we also measure these charge jumps. Correlations between those charge jumps and reconfigurations of the two-level systems that set the dielectric loss environment of the qubit, and seeing that there are correlations between reconfigurations of the TLS that can cause changes in the qubit T1 that are synced to those particle impacts and the offset charge jumps. I don't know if groups at IBM have looked at changes in the parity rate of qubits across large arrays or not.
All right, thank you. Maybe one last question that I'll ask.
Okay.
So in the phonon-mediated poisoning, do you know how much of the phonon transport is ballistic and how much is diffusive? So that, I guess that can inspire like mitigation designs, and you talked about like this micro machining substrate. So yeah, I'm curious about that.
Yeah, excellent question. This is exactly something we're working on right now, is trying to study the physics of this phonon propagation throughout the substrate both phonons that we would, inject, say, with a junction like this, but probably more importantly, or not more importantly, but maybe it's a little more complex problem to solve, is the phonons generated after one of these high energy particle impacts. So we are working with people from the particle physics community, in particular from the dark matter detection community, who they study particle impacts on dielectric crystals all the time to try to look for exotic dark matter particles, but they also need to understand the background events, things like gamma rays or muons hitting the chip, and know what the signal looks like. And so, yeah, the phonon propagation is non-trivial through the substrate. In a very crude way, it can be considered sort of ballistic when it's inside of the inside of the silicon. And at low energies, that's a very good approximation. It can be sort of ballistic after it leaves the junction until it hits a surface. But then at the surface, especially, say, I didn't mention it before, but this particular chip, without the copper on it, it's a single side polished wafer. So the backside is relatively rough. So the phonons are going to scatter at random angles. And same thing when they scatter off of, say, the niobium, if we're injecting below the niobium gap. So the angle is going to be getting randomized, but in between scattering off the top and bottom, and the sides for that matter, where the chip is diced, the angle is going to be random. So we think of it as a boundary limited diffusion between the injector, the source, and the qubit that's getting poisoned. Now, it's a little more complicated in the case of a high energy particle impact, because the phonons can also undergo scattering events inside the silicon, off of, say, isotopic impurities, or off of defects. There's anharmonicity in the crystal at really large amplitudes that can cause different kinds of phonon scattering mechanisms. And that is something active we're trying to start out right now. But the key idea of doing this micromachining still seems to have some promise. And I'll mention one of these papers down here. I believe this one was from some people in the superconducting detector community, was looking at suspending superconducting resonator-based detectors onto membranes. And so making membranes to make it difficult for phonons to get up into the membrane from the bulk substrate. And so that sort of approach might have some promise for qubits. So it may be some combination of micromachining of the backside of the substrate plus some phonon down conversion, whether it's from normal metals or from low gap superconductors, might be sort of the ultimate way to try to mitigate this poisoning issue from high energy impacts.
I see. Great. Thank you so much. I guess there are more questions in the chat. So yeah, thank you again. And everybody, we will be back after this, like in the second half of January, with our seminar series. I wish everyone have a happy holiday. Right?
Thank you.